H we will have to find out, and chi, for chi we will have to do some of the exercise. Right, now with this equation, if we do some permutation combination, then if we divide it by mu, remember we are dividing it by mu, chi by mu, or in another case it is m mu divided by h mu, right? Mu will be cancelled, so original equation that we will get back. So m mu, if it remains there, what is mu h? That is b. Or in another case, chi by mu is equal to m by b, right? But mu r has a typical relationship with chi. Chi is equal to mu r minus 1, and also mu is equal to mu 0 mu r, right? So if we substitute this value, that is chi by mu is equal to mu r minus 1 in the place of chi, and mu, that is mu 0 mu r, which is equal to m by b according to the first equation. So now what will I get? Mu r minus 1 divided by mu 0 mu r is equal to m we are given as 3400 and b we are given as 0.0048. So what is the ratio? It is 708.3 into 10 raised to 3, right? This is the ratio. Now using this mu 0 value, we can further go for the answer. It is actually 4 pi into 10 raised to minus 7 into this 708.3 into 10 raised to 3. Now what is the answer? Pi is 3.14. So here we can get as an answer for this particular ratio 0.8896. If we go further, we had mu r minus 1 upon mu r. So we can just expand, we can just say that it is 1 minus 1 divided by mu r, which is equal to 0.8896, right? So what will you get from this? 1 over mu r is equal to 1 minus 0.8896, that is around 0.1104, right? So what is mu r from this? That is 1 divided by 0.1104, and the answer is 9.0579. Mu r is equal to 9.0579. Okay, the first answer, that is the relative permeability of the material, is 9.0579. And how will we get b? B is equal to mu h. So that says that h is equal to b upon mu, and we have mu 0 and mu r. So now we can get h is equal to b divided by mu 0 mu r. B is what? 0.0048. Mu 0 is 4 pi into 10 raised to minus 7, and also we have found mu r as 9.0579. So what is the answer? H is equal to 421.914 ampere per meter. So we were given two quantities, and we have found another two quantities in terms of H, that is magnetic field, applied magnetic field, and the relative permeability 9.0579, that is mu r. Okay, so here is the end of the examples. Now we will move to the slideshow again. Okay, we had divided the materials in total 5 types. Those are diamagnetic, paramagnetic, and again ferromagnetic and anti-ferromagnetic and ferrimagnetic materials. There are 5 types of magnetic materials, right? Depending upon their dipole moments, we can classify them in 5 types. We have actually also seen the different magnetic properties: materials which are magnetic but with unpaired electrons, and magnetic which are non-magnetic materials, or say diamagnetic materials, where all the electrons are paired up, right? So using this, we can divide them in 5 types. First, here we have shown the magnetic dipole moments of the paramagnetic materials. Then the second one is ferromagnetic materials. We can see the difference between the directions of the paramagnetic and ferromagnetic materials. First, paramagnetic materials, they are randomly oriented. In ferromagnetic material, without any application of the field, we can see that they are oriented in a particular direction. And here in antiferromagnetic, they are oriented in the different directions, rather than one should say they are oriented in opposite directions to each other. Here, what have you seen in the last one? That is ferrimagnetic material. In antiferromagnetic material, the dipole moments have similar value, that is the magnitude remains the same, but the direction becomes opposite. In ferrimagnetic material, the magnitude changes by some fraction. So the opposite directions are there, the dipole moments directions are opposite, but the magnitude changes by some fraction. You can see in one direction the magnetic moment, the net magnetic moment is not 0. So overall net magnetic moment has a particular direction. Now we can see the differences for major 3 magnetic materials: ferromagnetic, paramagnetic and diamagnetic. What is the state? Generally ferromagnetic substances are solid materials, and paramagnetic, they may be solid, liquid or gaseous. The same way diamagnetic materials are solid, liquid or gaseous. Here I want to just remind that in our last lecture I have emphasized upon one major point, that all the magnetic materials have diamagnetic properties in them, but depending upon their dipole orientation, they may behave as paramagnetic or ferromagnetic. So the dominating properties which may become paramagnetic or diamagnetic ferromagnetic material, but there is a very suppressed property in them, is the diamagnetic material. Okay, diamagnetic property. Second one is the effect of magnet. The effect, when I applied the external magnetic field, the ferromagnetic material, they are strongly attracted by the magnet, but the paramagnetic material, they are feebly attracted by the magnet. And on the other side, the diamagnetic material, they are feebly repelled by the magnet. They will oppose the external magnetic field. Now the third point on which we can define the differences. Third point says that behavior in a non-uniform field. So when we apply the field which is non-uniform, we can apply the magnetic field by 2 ways. One is uniform magnetic field, that is flowing, the magnetic field lines are uniform in all directions, and here we are talking of the field which is non-uniform, the ferromagnetic substance that shows the movement from low to high field region, while the paramagnetic substance behave the similar kind of way. They will move also from the low to high field region. But diamagnetic material, they will move from high to low field region. The next point is behavior in external magnetic field with lines of induction. Here the density of lines of induction in the material is larger than the density of the line of magnetic intensity. This is true for ferromagnetic substances, while in paramagnetic substances, the density of the lines of induction is slightly greater than the lines of magnetic intensity. But in diamagnetic substances, it is quite a different. The density of the line of induction is little less than the lines of magnetic intensity. What is the next point? Next point is the effect of temperature on ferromagnetic material. At above the Curie point, a ferromagnetic substance becomes paramagnetic, while for paramagnetic substance, with the rise of the temperature, it is becoming a diamagnetic material. And what about diamagnetic material? There is no effect of temperature on the diamagnetic substance. Now, what about permeability? For ferromagnetic substances, the permeability is very high. Here, paramagnetic substances, it is slightly greater than unity, 1, and diamagnet, it is less than 1. The susceptibility chi for ferromagnetic substances, it is very high and positive. For paramagnetic substances, it is slightly greater than 1 and positive. But for diamagnetic substance, the susceptibility is negative. So these are the measures by which we can distinguish diamagnetic, paramagnetic and ferromagnetic substances from each other, right? These are very important from the from the properties point of view. Okay. Now this shows the graph of the susceptibility and temperature. Here in the previous slide we had shown the effect of temperature on ferro, para and diamagnetic substances. But here is the graph. The graphical figure shows here that for say the anti-ferromagnetic material, you can see that there is a nil point. Up to nil point the susceptibility increases as temperature increases. But after the nil point it decreases as temperature increases. The same way for paramagnetism, for paramagnetic materials, it constantly decreasing with the temperature increase, right? And for ferromagnetic substances, up to Curie point, the material susceptibility decreases up to a certain level. But as and when the Curie point is reached, you can see the behavior. It exactly acts as the paramagnetic material. The graph exactly goes parallel to the paramagnetic material. Okay. Now we have seen this slide before. It again shows the random orientation of paramagnetic material, but in the view of this we can have the periodic table. Here is a periodic table stating all the atoms, all the elements, but you can see that there are different colors in the periodic table. They show the types of magnetism at room temperature. You can see that here on this right hand side of the table, most of the elements they are shown in the green color. So they show the diamagnetic properties prominently. Here this Fe, Co and Ni, these three, they show the ferromagnetic property, and on the left hand side most of them are say paramagnetic materials, and one material which is shown here, that is chromium, that is anti-ferromagnetic material. So on the elemental view, most of them are paramagnetic, some of them are diamagnetic materials, and one or two are of them they are ferromagnetic materials. One can say that if we want to make some ferromagnetic compounds, even then we can make from the ferromagnetic materials, ferromagnetic elements. Okay. So now we will move ahead for a very important property of the magnetic materials, or say ferromagnetic materials, by which we can find out another properties of the ferromagnetic materials. We have shown that when magnetic field is applied, what is the behavior of the ferromagnetic material? It will be showing some kind of magnetization. Rather, I should say it will be showing some kind of permanent magnetization. So what is hysteresis? Hysteresis, when you hear the word, you will remind the word of history. You can see the effect of history in this. Hysteresis is the phase lagging of magnetic induction B in ferromagnetic and ferrimagnetic materials with respect to the cyclic variation of the externally applied magnetic field. So basically this is the effect due to the externally applied magnetic field. Here the specimen is kept below its Curie temperature. That means it is specifically for the ferromagnetism shown by the material. We are not moving ahead of the Curie's temperature. That means we are not talking about any type of paramagnetism shown by the material, right? Now what is the hysteresis loop? For this we will have to think about a graph which is B versus H. For this, for a while we will move to the tabletop. it's a B versus H graph, or in short we can call it BH curve of the material. You can see on the y axis B is there, on the x axis H is there, right? And with this we can, if we increase H, what will we get? We can get this type of initial increase in B, right? And here with further increase in H, the magnetic field intensity increases, magnetic flux density of the material increases, and if I increase H further, this will be constant. So this is called the saturation value of B. At this point the magnetization in the material will be saturated. So now if I increase further the external magnetic field, I will get a constant value of B. If I further decrease this, the H value is decreased in negative direction. It will not trace its original path. It will be tracing the another path, and it will reach somewhere here on the y-axis. So this is called retentivity or remnant flux density, BR. Okay, now here H is 0, but B certainly has some definite value. So this is called retentivity. If I further increase H in negative direction, it will be reaching here where B becomes 0, but H has a certain value. So this value is known as HC, or say coercivity of the materials. This is retentivity, this is coercivity. With the further increase in H, the material is magnetized in reverse direction, and again it will reach to a saturation point. Again if I increase H, it will become again 0 at a particular value of B, and again the cyclic variation process occurs, one can reach to the original point. So this loop is called hysteresis loop for the material, right? There are some application of this loop for the ferromagnetic material. Now we will move to the slides for the further discussion. You can see here, as I told you, that there is a starting point